Okay. So limits, an intuitive introduction to limits. So limits are the foundation of calculus, which seems so artificial, I guess. But let x approach zero, but never get there yet. We'll act like it's there. Whatever. It's fine. So how can we learn to enjoy them? This is all Ms. York's notes, by the way. So this is her voice. So it's all about approach, just so you know. Limits are all about approach. So what is the limits? Our best prediction of point value that we don't observe, that we see getting closer, like a hole or an asymptote. How do we make a prediction? Usually zoom into neighboring points. So in Desmos, we'll actually use Desmos as well, or plug in numbers close to the limit. You could do that as well. Why do we need limits? So it gives us an estimate what we can't compute when we can't compute a result directly. We do use it often for derivatives also. That's the other reason why we need it. How we know we're right? Um, we're not really sure, but what we do know is that if we plug in numbers close, you can use that to estimate the limit. Limits ask us what if we can directly observe a function at a value like x equals 0, x is growing infinitely. We don't need a prediction. The limit wonders if you can see everything except a single value, what do you think is there? So what do you think it's approaching? Like horizontal asymptotes, right? Like we don't know what it's exact going towards because it just gets closer, like say like y equals 2 or something like that. When our prediction is consistent and proves the closer we look, we feel confident in it, and the function behaves smoothly, like most rule functions do. The limit is where the missing point must be. Okay, so just some little blurb there. Now, geometric approach. If we're going to approximate the circumference of a circle using a primitive inscribed polygon, even without computation, we can observe the number of sides. As the number of sides increases, the better the approximation, right? So this is that's terrible. It's a terrible approximation. Because how many sides will have for that first one? N equals 3, right? This one's hard to tell, but if like n equals like, we'll say it's 12. I don't know. I'm just totally making it up. It's going to be pretty close. Um, so if in fact we can make the perimeter polygon as close as we please to its circumference by increasing the number of sides. And notice no matter how large the number of sides, it will never be the true circumference though. Like there's always gonna be a gap, right? It's hard to tell, but you can see a little bit of a white portion there. There's always a little bit of a gap. So you can make n equal like 100. It's still straight edges, right? It's not nice and smooth and curved. Um, so we think of it like a limit because we don't know. We're never gonna. And you guys probably might remember. Well, perimeter. No, I'm trying to think of angles. I'm trying to think of something else. Yeah, I'm thinking of something else. But what we do know, um, is that we can get pretty close to it. So as we increase the number of sides without bound, it's going to equal circumference of the circle. So the limit as n approaches infinity of the perimeter is a function of n, will equal the circumference. Circumference, is 2 pi r. And of course, that's going to be that's kind of a tricky way of thinking about it. I'm not even bother putting formulas. That was just think of visually, think of visualize what's happening. All right. So now let's actually get to the real stuff. Okay. So the notation. Um, so this right here is exactly the same what you see in quotes here. What is the function doing as x gets closer and closer to c? So it's easier to write in the notation, right? The notation is going to be an easier way of doing it. Or another way to think about the limit of f of x as x approaches c is L, if and only if fx becomes arbitrarily close to L as x gets close to c from either side. This actually is very important. We call this a two-sided limit. That's because we want to approach C from the right side and approach C from the left side. I think we already started talking about this notation last week, the C plus and the C minus, or the plus and minus as a superscript. So you're approaching C from the right side or C from the left side. And the hope is that they eventually converge at a certain place. We'll actually see that for example one. And the existence or non-existence of fx at x equals c is not relevant. We don't care about that. Um, whether f of c is defined is irrelevant for finding limits. I don't I don't care if I could figure out what f of c is. So like if like f like for example one, right? Can I find f of two? No, because you can't divide by zero. It doesn't matter because all we care about is approach. That's all we care about is approach. So all we care about is approach. And this table, I think does a great job of exemplifying that or showing that. So we want approach two, right? From the left and from the right. So here's coming from the left. Well, Laura, go ahead. Yeah. Hmm? No, won't exist. They have to equal each other. They have to equal each other to exist. Yes, it's from the movie Mean Girls. Lone does not exist. I still haven't seen it yet. I gotta watch it. Okay. When I started teaching calculus in 2009. Yeah. People started, I was like, what are you guys talking about? Anyway. So here's what we're gonna do. We're going to, maybe Desmos might be a little easier. If you have a device, yeah, some of you guys have your devices out. Yeah, go ahead. We can, but we're not gonna do that yet. That's the algebraic technique. Let's hold on that. We're not gonna do that today. Today we're doing numerical and graphical limits. Okay. So here's what I'm gonna do. I'm gonna go to Desmos because I think Desmos is gonna be a little cleaner. And y equals, I already forgot the function, x squared minus 3x, x squared minus 3x plus 2. Oh, yep, and x minus 2. X minus 2. Okay, so it looks like a line. And actually, what I'm going to do also, let's call it f of x. Whoa, what did I just do there? F. Okay, there we go. So I'm going to do table, make a table. Okay. You guys know how to do tables in Desmos? Just cite table or click on it. So I'll do 1.75. Ah, hold on. Hold on. You didn't like that.
I think if you change
The Y1. Yeah, you're right. Wait, what? Hold on.
Yeah,
It will work? How come it's not telling me?
From two to the X1 X.
yeah.
Or
You just change the table. Change the table.
Change that. And then
Yeah, I'm learning so much now. But no, still not doing it.
Or you just write x equals 1.75. No, sure.
Yeah, I'm just gonna do this. That was my initial intention. There we go. I'm just gonna do that, guys. Sorry. Okay, just do that. I was trying to get a little too cute here. That's all good. All right, so we get 0.75, right? Okay, cool. So we get 1.75. Sorry, 0.75. My apologies. If I go back and type in 1.9, I get 0.9. What are you gonna predict is gonna be the third one? And the fourth one? And to what Charlie was saying, which, yeah, we could factor it. I mean, I know you guys are aware of factoring it. If you're factoring what's happening, those go away. So of course, if you plug in 1.99, you get that, right? But at 2 is undefined. And if I go back again, if I plug in like say 2.001, 2.01, 2.1, or 2.25, whoa, I get 1.25. So I get point. Let's go back one more time. Yeah, 2.01. Yeah, so I get 1.01, 1.01, 1.1, 1.25. So you see, as we approach, what would the limit be? What would you say? 1, that's it. Now, can it exactly equal 1? No, doesn't exactly equal 1. And you can't plug in 2 anyway. But numerically and graphically, see what's happening. And if I were to zoom in on the graph, you can see it puts a little hole there, undefined. But see how like it's really close, like 1.9, you have all that stuff over here. It gets really close to 1. And when you're spot on, boom, there you go. So yeah. Um, so that's kind of like the main concept of a limit, numerically and graphically speaking, what's happening. All right, so now piecewise functions. These are fun ones. We kind of know what to expect. I'll just do a quick sketch here. It's supposed to be like graphing y equals x minus 1, I think. Correct, right, correct. And yeah, we plug in 2, you get 1. Plus you. Okay, so I take the limit as x approaches 2 of f of x. What are you gonna say? 1 still. Even though, what f1 equal? Sorry, f of 2. We don't care. We do not care. Why? Why do I not care? It's all about what again? Approach. I do not care what it equals. Limit has no. It's all about the approach, right? Yeah, progress, not perfection. That's a great way to think about it, right? Progress, not perfection. Like you always keep making progress out of it. Yes, anyhow.
Like what you're approaching with, like when I'm getting closer to the one, that where is my black going?
Yeah. Now we are going to talk about continuity later in this unit. And this will not be continuous because you'd have to take your pen or pencil off the paper or your stylus off the screen to plot that extra point. We'll have that discussion later and we'll talk about limits again. But yeah, just from a graphical perspective, yeah, that's all that's happened. Okay, so some other things, some implications. We already mentioned this. The left and right hand limits are different. If that happens, then you go Mean Girls. What do you think that stands for? Does not exist. Yeah, does not exist. It doesn't matter at all what the y value is. Again, it's all about approach.
One of these states
And what the limit equals is a number. No, infinity is not a number. So you could also say, you could technically say DNE when the limit's infinity, because what is infinity, right? It's this abstract idea of a number that keeps getting larger. And you guys know tangent, right? Like, tangent had these asymptotes here. The graph looks like this. We know this. So what's that limit going to be? Pos infinity, or if you say it does not exist, you'd be right. You'd not be wrong. You can say that does not exist. Let me clean up a tad.
Negative infinity or?
You are right, because I forgot how to graph tangent. After all, we are pre-calculus, right? That's why I teach you guys this stuff. You're correct. My apologies.
No, you were right.
I was right. Kingston, you're wrong.
Wait, but isn't it x approaching the negative?
Pi over 2 from the left side.
Wait.
Approaching pi over 2 from the left side.
The negative sign right next to it means the pi over two.
From the left side, yeah.
Going this way.
Correct. You know what that means? So you approach values less than pi over 2. Pi over 2 is 1.7 approximately. So we have 1.4, 1.5, 1.55, whatever, whatever, 5 something.
Oh, but I thought it approaches it from the other side. Like
That's pi over 2. That's plus.
That's plus.
It's plus, correct.
So the rules out on the left hand and right hand, and then I see the virtues. So there's no limit.
Right.
It only applies if that which specify that it would.
Correct.
Can you explain it? Like, so it goes.
So you're approaching from the left side. So like pi over 2 is like 1.57. So what if x is 1.5, 1.51, 1.52, 1.53, 1.54? So as you get closer and closer, right, to pi over 2, what's y doing? Up. That's why the limit's positive infinity. Because you have the superscript minus.
Is that all going into the right side?
Oh, that means you.
Pi over 2 minus, it needs to come from the left side. The values of x are less than pi over 2.
It's a negative.
Yeah. Sure. That's why you gotta pay careful attention to the tape. That's why attention to detail is so crucial in this class, in calculus in general. Well, yeah, let's talk about it. We got plenty more to practice. Let's do it. Actually, ooh, this is a good one. This is a really good one. Homework's gonna be kind of like this. This is nice. All right. So this is what we call a right-hand limit, because you're approaching 0 from the right side. That's the left-hand limit for part D. That's the right-hand limit for part E. The rest are all two-sided limits. F of 0 coaches F of 0. That's easy. That's 2. Right, that's easy. If you're approaching 0 from the left side, sorry, from the right side, what's y getting close to? And in general, now part B is what I call yeah, still 0. Part B, now, just getting a little OCD about my arrows. I was super OCD during the game yesterday. That was a nutty game. This guy still keep talking about it. Okay, two-side limit. When you don't see a superscript, it's a two-side limit. So we need the LHL to RHL for the limit to exist. Now, what if we approach 2 from the left side? What is it heading towards? 4. 4. Now, do I know precisely? No. I know it's like 3.999999999. I could just say, oh, I dropped dead. right? Not for a while. Okay, 2 from the right side, what's it getting close to? Actually, it does hit spot on. It's 1. But that does not exist because the LHL does not equal to RHL. They have to equal each other for limit to exist. And of course, 3 is just whatever. Sometimes there's whatever, like, oh, just find the Y value. It's 1. Sorry, 0. I can't do coordinate geometry. Okay. Hope that makes sense. Yeah, very good. Yeah. Yeah. So put 0 from the right side. So say let's pick a number bigger than 0, like say 1. And I do like 0.9, 0.8, 0.7, 6, 5, 4, 3, 2, 1. As I get closer, I'm getting closer to that hole, right?
Oh, so
I'm not getting spot on, just close. Now, part B is just saying 0 straight up. So I gotta look at both left and right sides. And they're both going towards the same destination. It's kind of like, for example, it's kind of like if Sydney's up in San Francisco, I'm down in San Jose, we're gonna meet somewhere in the middle, so we'll meet in Redwood City, right? Fine, we'll pass by each other. We're approaching. He's going south to me, I'm going north to it. But say, for example, he's going south, but I said I'm just gonna head towards like Hayward or I don't know, Modesto. Then, or we're not gonna meet, right? We're gonna be at different places. So it's all about you trying to get to the same place. Okay. Now, when the limit does not exist, ooh, some good ones too. More good ones. Okay. More good ones. All right. Now, I don't remember if we did this graph. Maybe we did. I don't remember in the first semester.
I'm gonna write on where it down fire. And like smell it, smell it, should I do it on? Because it's gonna all take it was literally.
That's actually a piecewise function, guys. So so if you think about it, if x are positive, you don't really need the absolute value, right? Who cares? Or if x is positive, fine. Just say x or x. It's 1. However, this is the part that's tricky. If x is negative, you have to replace the absolute of x with negative x. Because if x were negative, then you have to take the negative of it to make it positive. Like if I plug in -2 for x, what's absolute negative 2? 2, right? So you could replace absolute with negative x and still guarantee a positive outcome. But of course, it simplifies to -1. So when you graph it, the graph looks like this. And by the way, is it defined at 0? Nope. Undefined. So in this case, let's do my limits. What's my limit as x approaches 0 from the left side of fx? What's my limit as x approaches 0 from the right side of fx? They're not the same. LHL, it's not equal to R. I'm gonna close the door. It's getting loud. LHL is not equal to RHL. So the limit does not exist. So hopefully that makes sense. You can look at the graph. The graph's a great way of looking at it. You can plug in numbers if you want. Plug in like 0.1, 0.01, 0.01, -0.1, -0.01, -0.01. You can do that also. Or if you just think about algebraic, which I just did, the piecewise breakdown. Yeah, you get that. Um, so I kind of dissect this, I think, as much as I could. But graphically, I think probably hopefully that's the best way of seeing it. Graphically speaking, does that make sense? And you guys see why the graph is the way it is, based upon how AppSci is supposed to behave. And again, quick and easy way, always a surefire way, plug a number close to 0. 0.001, negative 0.01. You should get 1 and negative 1.
Left half like the third quadrant, so isn't it like, well, if
Well, my x values are negative, my y value is negative also. So I'm playing negative x values,
X over X, absolute
x
value.
over negative x, when x is less than 0.
But doesn't that make the absolute value make it?
Correct, but overall, it's going to reduce to negative 1. You have to have x over negative x. Overall, it's still going to be negative 1. So, right. Well, yeah, we have the top as well. Let's look at type 2. And by the way, when this happens, that's a jump, discontinuity. We're going to talk more about that later in the week. Type 2. That's going to look like this. So the limit, what's the limit of approach 0 from the left side? And if I do the other limit from the right side, what do I get?
Oh.
Right. So in this case, even though they're approaching the same thing, the thing's at infinity is not a number. So it's still unique. Now, if you said infinity, I won't hold that against you, though. You're still correct. I'll still give you full credit. Don't worry. But technically, is there a limit? Is there a ceiling? Sky's the limit, right? Like you hear that expression all the time. Like, I mean, just you can just go up forever. It's kind of like if you lift like a balloon, it just goes up in the sky forever. Like, okay, it does pop eventually, but
So it's the limit. They say that, and it's the limit on the way.
right. Now, of course, if one side's going towards infinity, the other side's going towards negative infinity, then of course say DNE, because that does not exist. This one's a kind of a wacky one. What's whatever X. Actually, I'll graph in Desmos for you guys.
What you could say anything.
Y equals. Okay, that is crazy. What's happening there?
So you.
Whoa. Or I'll zoom out. Yeah, it oscillates. So kind of looks like this here. Okay. That's kind of sloppy. That's like my 3-year-old drawing. Okay. Um, yeah, we call this an oscillating. And we don't really deal with this. I don't worry so much. It's just so you're aware. That's mainly because of the period of sine. What's the period of sine? 2 pi, right? But you're doing 1 over x. So things just get haywire as x gets closer to 0. Because like if you plug like 0.1 to have sine of 10, which is going to be in the fourth cycle, I think. But if I do 0.01, which is not that far from zero point 0.1, but then I'm doing sine of 100, which I don't know where that is in the cycle. And we know it goes back and forth. So it basically goes crazy, meaning oscillates. What's the highest value for sine output? Yeah, and lowest very rapidly as x approaches. That's what's happening, just going crazy. And by the way, my sketch was terrible because this would fail the vertical line test. Just so you know. I just, I had to have steady hands. Okay. So again, just kind of giving you kind of sort of the foundational stuff of limits. Okay, so it's all about approach, but I don't know what the heck this is approaching. It's just going crazy as I get close to zero. Now, find limits analytically. That's where really we need to spend most of our time on. Definitely. Do I see you guys tomorrow? No, for Wednesday. Yeah, we're gonna spend a lot of time with that. One thing you should always do is always substitute first. Sometimes just that simple. Like, isn't that just y equals 5? What's the y value of y equals 5?
Well,
So that's it. It's just 5. It's just that simple. Or here, if you have y equals x, just plug in 2. Yeah. Or here, y equals x to the 4 power. If you plug in 2, what do you get? Yeah. Sometimes just plug in. However, that's not always going to be true because I want to challenge you guys. Yeah, this would be too easy. It wouldn't be BC honors. I'd have to really. We're going to get some crazy problems. We'll do crazy on Wednesday and Friday or Thursday. Yeah, sometimes just plug in. Sometimes just do that. Yeah, sometimes just plug in. Questions? Okay, we're almost done the notes. This right here, I'm gonna tell you right now, just common sense. You don't have any? Oh, I'm sorry. Just common sense. Like, okay, if I have two functions being added and take a limit, fine. There you go. Or actually, let me back up a little bit. They're calling the limit for FL and limit for GM, so L plus M. Sorry about that. Yeah, just L plus M. If you have the individual limits, I think that's why I want to do that. If you have the individual limits, just add the two individual limits. That's all. But very important, they have to exist though, each limit on its own. Just add them. That's all. Or just subtract them. Or multiply them. Or multiply the constant. Or divide them. Granted, we don't want m to be equal 0. Or if raising the power, raise the power. Great. Right, not a big deal. So in this case, use above properties. We could decompose this and break it down to all the separate parts. Seriously, I'm not gonna waste your time. Just plug it in. I'm not using really the properties, I'm just plugging in. If you want to use the properties, you could like say, oh, I got, one function is 3 of x. The other function is negative 13. Or the function is 3x minus 13. The other function is cube. Yeah, it's just dumb. Just plug it in. Yeah, just plug x equals 5. Okay, we're pretty much close to being done because that's where I want to end things for today. So By the way, if you have a polynomial function, which I just did, then guess what? It's just f of c. If you have a rational function, guess what? Same thing again. So just make sure the bottom's not 0. F of c over g of c. So in terms of substituting is what we can do. That's fine, but may not work all the time. So we're going to talk about that tomorrow. Not tomorrow, sorry, Wednesday. But always try substitution first to see what happens. And yeah, there's some warnings, some like one-sided things and some fun, but we're gonna get the fun stuff happens on the next day. So we'll save that for when we get there. Okay. Homework should be this. I actually circled it and I try to call it homework number 3. So it should be spelled in Schoology. If not, I'll put in Schoology. Yeah, so just it says here to do it numerically. You can make a table and do a sketch. You can use Desmos for that. Here, just look at the graph for number 2. So very similar to what we did on the notes for that one. That's what's homework number 4, so don't do number 4. Yeah, I think that's it. I mean, it's pretty straightforward homework. Yeah. So anyhow, if you want to get started, if you just want to take a little break, it's all good. So.